Okay, let's talk about the programming project. There's a lot here. Where I want to start is with our solution. We are solving for T, the temperatures. We are solving for all the values in this matrix here, where this first column is our initial conditions, essentially where we start with. What is our initial temperatures? And if you look at the document, the first thing it says is pre-allocate T to be an n by n of 0, so make it all zeros. Populate the first column in the matrix with the initial condition. That's what that is. This is our initial condition. Then the rest of our temperature solver function is going to be filling in the rest of these columns, where each column is solved for using our equations above. So this is going to be called T2. It's our second set of temperatures. So at the end of the day, once we solve for all of these temperatures, we're going to see what the temperature is at every single node. Here's M nodes at every single time point. So if we look at our plate, we're looking at a radioactive plate. Radioactive means that it emits heat. It gives off heat. I'm looking at a cross section and I'm checking to see, okay, what is my temperature at each time point? So I'm breaking it up into however many nodes there are. 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes here. Okay, I'm saying, okay, at temperature 1, in column 1, I'm saying that it all starts at 25 degrees Celsius. And then, since my plate is generating heat, it's probably going to be hotter in the middle, since it's, I don't know. It's going to be hotter in the middle, maybe, because that's the most isolated. So we're probably going to think, okay, the temperature here is going to go up in some sort of form. It really depends on what's happening out here at the boundaries, out here at our edges. Okay, so at time point 2, at the second column, at T2, my temperatures are going to change. So I'm saying, okay, how did they change? And then again, at temperature 3, it's probably going to be a little bit higher, depending on what's happening out here at the edges. And I'm saying, okay, at T3, how does it change? And then I keep solving over and over and over again for T4, all the way down to Tn, for however many time steps I have. That is my solution space. That is what I am solving for. I am filling this matrix with my equations, one column at a time. So I start with my first column, it's just my initial conditions. And then I'm going to solve for my second column. Once I solve for my second column, then I will solve for my third column. Once I solve for my third column, then I will solve for my fourth column. And keep going until I run out of columns. The equations we use to solve for these temperatures differs depending on which rows we're talking about. So there's boundary conditions. Essentially, what happens at these edges here? We've got 4 different options. I don't remember off the top of my head right now, but I've got 4 different options. So I'm saying, okay, at my first node, right here, my first node, how does my temperature change? Actually, not right there. Right here, at my first node, I'm saying, okay, which equation do I use in order to calculate my temperature for that node? For my last node, right here, what equation do I use to calculate my temperature for that node? That takes care of what's happening here at the ends, at my boundaries, at my edges. Then I have an equation that tells me what's happening all in here. What happens in these, what we call internal nodes. So our equation that we use to do these calculations depends on which node we're talking about, on which row we're talking about. So let's look at the explicit solver equations. Let's look at the explicit solver equations. Where are they? Right here. Explicit finite difference equations. There's other equations above, like equation 2.3 that you'll need. You'll need equation 3.6. You'll need G dot, delta X, K, all that stuff that you get from your properties and from the equations above. Okay, I'm not going to talk about those. But here's our explicit solver equation. If we look at this equation, it looks confusing. But essentially, we can just say it's essentially y equals tau, x1, plus 1 minus 2 tau, x2, plus tau, x3, equals, or plus some constant, plus c. That's essentially what it is. Let me move it. This is what this equation boils down to. It just so happens that y is my next temperature. So here is my next temperature in the column over. And x1, x2, and x3, these are my temperatures in the previous column. So I'm saying T1 for, no, not T1. This is internal nodes. M equals 2 to 3 to M minus 1. So T4 at time point 2 equals, and I'm totally remove this, equals tau times T4 minus 1, which is 3 at time point 1, plus 1 minus 2 tau at time point 1 at node 4, plus tau T5 at 1 plus C. So you need to pay attention to what these superscripts mean, where they are in your matrix, in your temperature, in your solution space, and what these subscripts mean, so that you know where to get all of these numbers from. This is where you're storing your answer. So where are you storing the answer for the temperature at time point 2 in for node 4? And where are you getting these numbers from? Where are you getting these numbers from? Where does T13 located? Where is T14 located? Where's T15 located? And once you figure that out, then you can just go ahead and maybe write this equation a couple more times with a couple different more m values and n values, and you can start to figure out a pattern. Once you figure out the pattern, then you can go ahead and write your code in a loop. And that's essentially what the document tells you to do. Write it in a loop. But what we're doing is we're just filling that T matrix. T equals, column 1 is your initial conditions. And then you're saying, okay, I want to solve for T2. I want to solve my second column here. What equation do I use to calculate for node 1? What equation do I use to calculate for node 2? What equation do I use to calculate for my internal nodes? So here, identifying this is just a constant, this is a constant, this is a constant, this is a constant. But where are these numbers stored? Over here, these ones are already defined. You want to grab the numbers there. And then here is where you are storing it. Where do you want to put your final answer? So note, I mentioned the boundary nodes, the boundary conditions. These equations read the same way. If you can understand this equation, you should be able to extrapolate it to understand these equations. So T1 at 2 equals just a constant. T1 or Tm at 2 is the same constant or a different constant, TL. Okay, so just if you're confused with this notation here, then write it down with actual numbers. But these are just your unknowns. These are just your unknowns, but it's the same thing, identifying, okay, where is this number stored, or where should I store that? Where do I get this information from? So on your right-hand side, where are these values stored? Or where do I get these values from? And where do I store my answer? For the explicit method solver, we are literally doing it one value at a time. We do our internal nodes first. So we're saying, okay, calculate this one, calculate this one, calculate this one, calculate this one. Once you're done with all the internal nodes, calculate this one, calculate this one. We do it one at a time. Because in order to calculate the temperature at the second time point for node 4, all of these temperatures over here are already solved for. That is the explicit solver. That's the explicit solver. The implicit solver is doing the same thing. It's still solving for your next set of temperatures, but it's doing it by solving a system of equations. essentially what we're doing is we are saying T equals initial conditions, and then we are solving for all of this at the same time. We are solving for all of our unknowns at the same time using our matrix algebra, using our system of equations. So to solve for this, we need A T2 equals B, where this is our X. That's what we're solving for. So for this, we're going to go ahead and fill our A matrix. T is our unknowns. Call it X, whatever you want. Fill our B vector. T equals A left by B. So it tells you what you do. Okay, so we're solving for this entire column all at once. Whereas with the explicit solver, we are solving for one temperature at a time. That's the difference. Okay, so here's our equation for all of our internal nodes for our implicit solver. If I rewrite it, it looks like this. Negative T x1 plus 1 minus 2 tau x2 minus tau x3 equals some constant. Keep in mind, that's known. Figure out where it comes from. So all of these are constants, where x1, x2, and x3 are unknowns. Okay, this system, this matrix, this equation should look familiar to you. Okay, and we tell you this here is our coefficient in A. This here is our coefficient in A. This here is our coefficient in A. This here is in our B vector. It's just, once again, identifying where to store it in your A matrix. And this is what Lab 9 was aimed at, and Lab 10 is aimed at helping you write the code for the implicit solver. Okay? But these are just your equations. These are just your unknowns, your coefficients in your A matrix that you can use to solve for T. So this is x1, x2, x3. If I wrote this equation again, it might look like T1 x2 plus 1 minus 2t x3 minus tau x4 equals C. So once again, keep in mind, where do we store these numbers? What unknowns are they going to be, or what equation do they correspond to? Which unknown do they correspond to? Okay, so there's two matrices, A and there's T. Keep them straight. T is our solution. It's our unknowns. Okay. T is what we are storing all of our temperatures in. A is our matrix of coefficients. So it's full of our coefficients from our system that's put together with the implicit solver. So if I copy and paste those over, negative tau x1 plus 1 minus 2 tau. Oh, I'll put, instead of x, I'll put in the t. T, 1, 2. Plus 1 plus 2 tau, t, 2, 2. Minus tau, t of 3, 2. Equals some constant. We'll call it C1. And then if I did it again, negative tau T2 2 plus 1 plus 2 tau T3 2 minus tau T4 2 equals C2. Okay, so this is our system of equations where these go in to A. So our big A is how many unknowns do I have? How many equations I have? So keep in mind, when we fill our A matrix, equation 1, equation 2, equation 3, equation 4, etc., unknown, T1, T2, T3, T4. Okay, so pay attention to the difference between our A matrix and our T matrix. Our T matrix stores our solution, stores whatever we get when we solve for X. A stores the coefficients that we're going to use in order to solve for T, to solve for our unknowns. And like I said, Lab 9 was aimed at helping you guys figure that out, and same thing with Lab 10. Okay, some other things to note. Let's talk about this. So actually putting together your temperature solver function. Your temperature solver function has a lot of inputs. Number of nodes, number of time steps, the length of your plate, alpha, K, G dot, properties of your plate, dt, the time step, so that would be delta T. Your initial conditions, note your initial conditions is a column. It's that first column of T. And then BC1, P1, so this describes your boundary condition for your first node, M equals 1. These are the boundary conditions for your last node, M equals capital M. BC1 is just a number, 1, 2, 3, 4. BC or PM or BCM, number 1 through 4. P1 and PM are a little bit more complicated. Let's go ahead and look down here. So here's our options. Like I said, BC1 is either going to be 1, 2, 3, or 4. P1 depends on what BC1 is. If BC1 is 1, P1 equals that constant temperature. If BC1 equals 2, P1 is the value of the heat flux, whatever you call it. If BC1 equals 3, then P1 equals 0. And if BC1 equals 4, then P1 is going to be a 1/2 vector. And that is H naught in T infinity. So it has two values. So if you look at the equations used for your boundary conditions, I'll go up to the explicit. If you look at the ones used for the boundary conditions, essentially, you don't have an input called T1, but you have an input called P1. So if BC1 equals 1, then P1 equals T0 or T0. So keep in mind what P1 is, because it's different depending on what your boundary condition is. If BC1 equals 2, then P1 equals Q0. So now, instead of this being P1, now this is P1. So make sure you use P1 appropriately in your equations. Same thing with PM. Make sure you use PM appropriately. I can do this. There you go. Same thing with PM. Make sure you use PM appropriately in your calculations. Okay, so that's Temperature Solver. That's pretty much what I'm going to go over in this video. Hopefully it's helpful. Watch it as many times as you need to. But if you understand the difference between T and what we're solving for and how that differs from A using a system of equations, keep track of where your values are stored and where your values are coming from. If you can understand the array notation with the equation notation, it will help you solve your temperature solver or write the code for your temperature solver function.